Good morning, boys and girls. We meet again as we continue with our revision in preparation for the end of year examinations. And if you've followed through the previous presentations, you can pick up that we are explaining concepts, take them directly to a past paper and answer a question which is designed to test the concept at an examination level. So in the past few sessions, we looked at chemical equilibria, acid-base equilibria, rates of reactions, and now we are looking at electrochemistry, which usually comes as the last section of your typical examination paper. So you're going to notice that in the paper we are using as our reference, there are actually two questions, question 8 and question 9, each with 14 and 11 marks respectively. So that's about 25 marks, a lot of marks that can make a difference towards your final mark for the examination. So it means that it's very important for you to prepare sufficiently when you are answering these questions, because they are very tricky and they come with a lot of practical applications which you are supposed to show as you will be attempting to answer those questions. So here we are talking of electrochemistry, and by the end of this section we are expected to know how to balance oxidation and reduction reactions, how to represent, interpret, and perform some calculations around galvanic cells, and show an understanding of standard reduction potentials, and also how to determine cell potentials, electrical work, and free energy, and also extend all that to the dependence of cell potential on concentration. So if this can be expressed in terms of an equilibrium, how do we keep track of the flow of electrons in the solution and the amount of electrical work that is done, and then use those concepts to express the mechanism or the operations of batteries, and how we can use electrochemistry to explain corrosion, and the industrial and practical applications of electrochemistry in electrolysis and the commercial electrolytic processes which are used both in industry, in our day-to-day lives. So to start by a few technical definitions, I'm not going to go much into the definitions because you were introduced to electrochemistry in grade 10 and a great deal of details were explained in grade 11. So by now we expect you to know how to define technically, if you are to be asked what is oxidation and what is reduction, and from those definitions you are supposed to be able to make representations of redox reaction. So just to give you a quick recap, we are saying reduction, it's a gain of electrons. So any species that react by accepting or receiving electrons, we say the material is undergoing reduction. While oxidation, we technically say this is loss of electrons, where we are saying any material, be it an individual atom or a molecule, which during its reaction loses or gives away an electron, we say it is undergoing oxidation. So put it in simple terms, I think by now you should be seeing this, that oxidation is loss of electrons, while reduction is a gain of an electron. Here are a few examples of redox reactions. meaning that oxidation and reduction reactions taking place concurrently. Now you also find out that redox reactions cannot take place in isolation, because during chemical reactions we can only say a chemical reaction is taking place when there is exchange of electrons between species, meaning that electrons are not released into the vacuum or into the atmosphere. They have to go somewhere where they are picked up. That's how nature works. So you'll see that at any given moment where you are making representations of reduction, there is a concurrent oxidation process taking place. So let's take, for example, here we've got zinc as solid reacting with copper sulfate aqueous. When we are talking of copper sulfate aqueous, we are talking of copper sulfate that has been dispersed in water, meaning that we expect copper sulfate, when it is aqueous, it means that it exists as ions like this, which are dissolved in solution. Okay, so if you are to crystallize this or remove water, you will see that the opposite and equal charges will attract each other and form a solid copper sulfate. So it exists as a solid, and it is readily dissolves in water to give you an aqueous solution of copper sulfate, a blue solution. Okay, so here we are saying that zinc, it's a solid, not an ion. Put it in a solution where you've got copper ions and sulfate ions. Zinc has got a capacity to go into solution, give away electrons, become an ion, replace copper out of the solution, such that where we had copper sulfate, it becomes zinc sulfate, and where we had copper ions, the ions are taken out of solution and gives us some brown particles of copper solid. So what exactly is happening? So as you can see from that representation, the copper is in a 2+ state, meaning that it has lost 2 electrons, while the sulfate species is carrying a 2- a negative charge. So what it means is that this zinc solid is now exchanging its electrons with copper. So it gives away 2 electrons, and those 2 electrons are picked up by copper. So copper changes from being an ion into a solid, while zinc changes from a solid into an ionic species. A similar phenomenon can be represented between the reaction of copper as solid plus silver nitrate, and it will give us copper nitrate plus silver ions. So this is a mistake. It's not supposed to be copper sulfate. It should be copper nitrate. Copper, in other words, we are saying the copper gives away 2 electrons to silver, but 1 silver ion can only pick up 1 electron, so we'll need 2 of those to balance up the charges, and then we'll have copper going into solution and 2 silver atoms coming out of the solution. Here's an interesting one which always come in an exam, and when they bring this in an examination, they expect you to know how to keep track of the flow of electrons as they are moving around between these species. So take a closer look at this, as we will be making some interesting deductions of what is happening here. So you'll see that this is manganate, the manganate ion, and we've got 5 ion 2+ ions. And the interesting thing here, we've got the H+. What does the H+ automatically tell you? It tells you that this reaction takes place in an acidic medium. So I want to emphasize that in an exam, they will tell you that show the redox reaction taking place between the following species in an acidic medium or a basic medium. So what does that mean, or how does that affect you in terms of your interpretation and application of the redox process as the medium is changed like this? So you'll see that in an acidic medium, the manganate is in the oxidation state of +7 electrons. So we are saying the manganese in this case has got a charge or the oxidation state of +7, and it's reacting with 5 ions, and each ion has got a charge of +2, and then we have got 8 protons. The 8 protons, which shows that we've got, it's in an acidic medium, but it also plays an important part in terms of the transmission of electrons in the solution. So we are saying after the reaction, the manganese changes from 7+ to 2+, meaning that it has gained electrons. So in this case, we are saying manganese 7 has been reduced by picking up electrons, and its oxidation state has changed from +7 to +2. So where did it get those electrons? It used to undergo oxidation. So, but before I go any further, I want you to pick up something interesting. You see, we have got oxygens, 4 of them, and these 4 oxygens have received 8 foreign electrons. So the 8 foreign electrons gives us 4 oxygens, which are 2-. Okay, and here we've got 8 H+. So you see that automatically the 4 or 2- are going to combine with 8 H+ in a ratio of 2:1 to give us 4 water molecules. So here is an interesting factor. We are saying this is already an ion carrying a positive charge, meaning that the 8 hydrogens, they are not losing electrons any further because they have already lost the electrons. And the oxygens, they are not gaining electrons from anywhere because they are already breaking away from the manganate ion with their negative charges or the extra electrons they have received. So the only thing that is happening here, we are saying it's just a rearrangement of the oxygen. So in other words, while the manganate ion is undergoing reduction, the H+ is undergoing oxidation to give us that. So here's the interesting thing, what is now happening with the ion 2+. So the ion here, it was ion 2+, but in our example, in our final product here, the ion is now 3+, meaning that each ion is going on to lose a further electron. That's why its oxidation state is increasing from +2 to +3. So it is those 5 electrons, each coming from one of the Fe2+, which are going to move on to the manganese 7+. And when the manganese pick up those 5 electrons, its oxidation state is reduced from +7 to +2. Are you following me, boys and girls? Because this is very, very important. And you see that we are going to go on to do half reactions, which when we are doing cells, we are going to show electrode potentials or half electrode reactions of what is happening there. So it means that this background interpretation of a representation like this is very, very important, as it will help you to make sense of the electrochemical reactions taking place there. So let's make a quick review of what we are talking about. We are saying oxidation, reduction, put together, it gives you redox reactions. It involves transfer of electrons from the reducing agent to the oxidizing agent. So in an exam, they can ask you, define the following terms: a reducing agent. So a reducing agent or an oxidizing agent, it is the opposite of the oxidant or the reductant on its own. We are saying oxidation simply refers to the loss of electrons, while reduction is gain of electrons, and a reducing agent is an electron donor, while an oxidizing agent is an electron acceptor. Okay. So like I said, in as much as we can represent a whole redox reaction, but for us to go into the fine details of accounting what is exactly happening at each and every stage of the redox reaction, it is important for us to be able to represent half reactions of the reaction. And how do we do that? Like this. So we are saying the half reaction method, you take the overall reaction and split it into two. Where and how do you split it? We are talking of, you put reactants on their own side and then the products of the reactions on the other side. So you separate that reactants which are undergoing oxidation, and then you deal with them, and then those reactants which are undergoing reduction, and then you deal with them, and then the products of those individual reactions, you combine them to give you the overall product of the reaction. So like for example here, we agreed earlier on that manganese is undergoing reduction. And how is it undergoing reduction? The H plus is strong enough to come and snatch all the oxygens away from the manganate 7 plus molecule. And when it does that, the manganate is not going to remain as a freestanding species with a very high charge of 7 plus. It is facilitated by the coming in of 5 foreign electrons. So the hydrogen and oxygen forms a water molecule, while the manganese pick up the 5 electrons and form manganese 2 plus. And then the oxidation process, we are just simply having the 5 ion 2 plus ions, each losing 1 electron. So a simple representation of that phenomenon is like this. So we are seeing that it is 5 electrons which are being generated here, which are being picked up over there. And then if we combine these half equations, it will give us something like this. Okay. So the half reaction method for balancing equations for oxidation reaction also occurs here in an acidic solution. So that's why I was emphasizing the role of H plus ions in this reaction. So we are simply saying that you write separate equations for the oxidation and reduction half reactions, and then for each half reaction you balance all the elements except hydrogen and oxygen, and balance oxygen using water, and balance the hydrogen using H plus, and then you balance the charges using electrons. That's very simple and straightforward, and I expect you to know how to carry out that. Okay. So when you are also doing the half reaction, you can write separate equations for oxidation and reduction reactions, and then for each reaction you balance all the elements. Okay, we have already talked about this, and then we're saying after balancing the charge using electrons, if necessary you multiply one or both balanced half reactions by an integer to make the numbers of the reactions in both half reactions equal. And then when you've done that, you see that if you add the half reactions and cancel identical species, you have a complete full redox reaction with balanced quantities both on your left side and your right hand side. Okay. So here's an example, a typical examination example here, which we are going to use to follow the steps we have highlighted just now. you have got a chromate ion. So let's deal with this chromate and understand it electrochemically. How do we determine the oxidation state of chromium? And there are two of them, eh? You look at your oxygens, we know it's given that come hail, come thunder, oxygen will only react or participate in a reaction in which it picks up 2 foreign electrons. So we've got 7 of them, meaning that we need 14 electrons to feed to these 7 oxygens. Fair enough. So are we saying the 14 electrons are all coming from the 2 chromium atoms? If that's the case, it means each chromium atom is making available 7 electrons. But that's not the case, because in this whole species, we also have 2 foreign electrons. So those 2 foreign electrons reduces the number of electrons which are supposed to come from the chromium atoms. So where each chromium atom was supposed to make 7 electrons available, it will now make 6 electrons available. So what does that imply? It means that each chromium atom in this ion is making 6 electrons available in stabilizing this dichromate ion. What about in the sulfurous or the hydrogen sulfate ion? So you will see that we have got an H plus and a sulfate SO3 minus, and they are balancing off because of their charges there. But the final product of this species is such that the chromium changes to 3 plus, and we still have our hydrogen sulfide. So the question is, how can we balance up this equation? Because obviously this is not balanced up. Where are the electrons coming from? Where are they going? How, when, and where? So the first step, you need to separate half reactions. So the half reactions, they are such that this is going to undergo a reduction process, while this is going to undergo an oxidation process. And remember the steps we highlighted earlier on, where we said you first need to balance up the oxygens by forming a water molecule, and then all the other things follow. So here we are saying balance elements except hydrogen and oxygen. So let's see, how do we do that? There we are. So if you look back here, something is not right. We've got 2 chromiums, but we've got only 1 there. Okay, so how do we sort it out? We account for the chromiums equally. So you've got 2 chromiums there and 2 chromiums there. Okay. And then what about our hydrogen sulfide? Here, if we've got HSO3 minus, something is not right. So you need to bring in another oxygen to make it HSO4 minus. Okay. So how many electrons are needed to balance the charge in each half reaction? So you can actually see that here, without preempting, we are seeing that chromium is changing from 6 plus to 3 plus. So each chromium atom is going to need 3 electrons. So if it is going to need 3 electrons and we've got 2 of them, that means we need a total of 6 electrons coming from somewhere to come and reduce this chromate ion. So here we are bringing 6 electrons to the chromate ion so that we create 2 chromium 3 plus and 7 water molecules. So for these 7 water molecules, what it means is that we need 14 hydrogen atoms, or hydrogen ions, which are coming as H plus. Because remember, when our oxygens are moving away from the chromate, they will be going already carrying their 2 plus ions. Okay, so we need 14 of the H plus to cater for the 7 oxygens, 2 plus minus. Okay, and then here we can actually see that where we have got a water molecule plus SO3 2 minus, we can actually end up having a H2H plus this is missing this 2H plus here, plus SO4 2 minus plus 2 electrons. So how can we balance the hydrogen atoms? This is how we balance them. So we are saying, so for this reaction to occur in an acidic environment, we need 14H plus 6 electrons to give us plus the chromate to give us 2 chromium 3 plus 7 water molecules. And then for this, you see that we need the 2H plus, which was missing. So how can we balance the electrons now? So we balance the electrons by now saying 14H plus 6 electrons plus this. So since in this expression we are generating 2 electrons whenever we have the HSO3 minus turning into an HSO4 minus, and generate 2H plus, we also get 2 electrons. So to account for it, we are saying we multiply everything here by 3. This whole expression by 3. So this becomes 3 water molecules, 3 HSO3 minus, 3 HSO4 2 minus. So 3 times 2, it gives us 6 electrons plus 2H plus, it will give us 6H plus. Okay, but we need them to be 14. So somewhere where the other 2 have to come from somewhere. Okay, so the final balanced equation will be such that we've got the dichromate plus 3 hydrogen sulfate plus 8H plus to give us 2 chromate 3 plus 3 HSO4 plus 4 water molecules. Okay, so you understand how this goes on as we do the next step. So here's another simple exercise where you balance the following redox reaction in an acidic solution. So in a similar manner, you just follow those steps which we've highlighted earlier on. First, deal with your reduction quantities and your oxidation quantities, and see that how many oxygens do you have, how many water molecules do we have, and then you balance it up like that. In a similar manner, where you've got the chromate reacting with hydrogen peroxide, you also play around with those quantities in a similar manner, like that. So we are simply saying that you can also equally use the half reaction method for balancing redox equations in basic solution. How do you do that, and what's the difference here? We are saying if you use the half reaction method as specific for acidic solutions to obtain the final balanced equation as H plus ions were present. So in other words, you just repeat the very same thing we have done with H plus ions, but the only difference is that you are replacing them with an OH minus. So to both sides of the equation, add a number of OH minus ions that is equal to the number of H plus ions present. So you want to eliminate H plus by turning it into water. So from water on the both side containing both H plus and OH minus ions, and eliminate the number of water molecules that appear on both sides of the equation, and then you check the elements and charges that are balanced. So let's take a look at an example which we can use to represent this phenomenon. So here's one example where we are saying balance the following reduction in a basic solution. So we've got bromine, a bromine molecule, and an OH minus in aqueous solution. I want you to see how things are going to change here. This bromine is changing into a bromate ion plus a bromide ion and water. And you are given another example where you've got the chromium hydroxide reacting with an OH minus in a basic environment to give you a chromate 3 plus water. Okay, so how do you go about this? We are saying with all these applications we have explained, we can go on to use this phenomenon in the applications of electrochemical cells. And how does that help us? If we can master the technique of dealing with half equations for an oxidation and for a half equation for reduction, it means that when we take it to electrochemical cells, we know that at an electrochemical cell, one of the electrodes, there is oxidation taking place, and one of the electrodes, there is reduction taking place. So your ability to account for the electrochemical activities taking place at each and every cell, you can represent the flow of electrons in the whole electrochemical cell and see how you generate an electricity. Okay. So for that reason, you will see that we are going to use these kind of interpretations to represent electrochemical cells. So let's take, for example, if I can quickly take you through this, where we are. I want to use more examples. So we are simply saying that in electrochemistry, we are using electrochemistry to study the interchange between chemical change and electrical work. Okay, and where we have got electrochemical cells, we use systems utilizing a redox reaction to produce or use electrical energy. And how do we do that? We consider the redox reactions where we transfer electrons through the processes we have highlighted earlier on, and we assign oxidation numbers, which are imaginary charges, which we have to balance up as we are carrying out the reactions of the material. So what are oxidation numbers? We are saying these oxidation numbers, they are imaginary charges. So these imaginary charges, there is a method of assigning them to species in a reaction, in a represented reaction. So like, for example, a pure element has got an oxidation number of 0. In other words, what we are saying is that it has not gained or lost electrons, so it is neutral. While a monoatomic ion, an individual ion, it has got a specific oxidation number which is assigned to it depending on how many electrons it has given away or received. While a neutral compound, it's a sum of all the oxidation numbers of the individual atoms in the compound, and it adds up to 0. While a polyatomic ion, you will see that it is the oxidation number of the ion's charge, and negative oxidation numbers generally assigned to more electronegative elements, meaning that you must have a clear clue of what's happening on your periodic table and how you classify materials from your left going to your right as you account for electropositivity through to electronegativity on the periodic table. Okay, so like, for example, for a hydrogen atom, you always assign a +1, and when it reacts with metals, it forms a metal hydride, and the hydrogen will carry a -1 in that instance. And oxygen, it is under normal circumstances always assigned a -2 in most cases, but only in peroxides, that's when you assign it a -1, and where it reacts with fluorine, that's when you assign it a +2, for the primary reason that here oxygen is less electronegative than fluorine. So fluorine is highly electronegative. So it will actually pull electrons away from oxygen. And then the oxygen will suffer loss of electrons, and hence it will become positively charged. fluorine, come hail, come thunder, is always -1. Okay. So, as we have agreed that oxidation is loss of electrons, and oxidation numbers increases or become more positive as more electrons are lost, while reduction is a gain of electrons, and oxidation numbers decreases as or become more negative. So in other words, we are saying oxidation involves loss, oil, reduction involves gain, rig. So from now onwards, you can play around or come up with your own catchphrase for oxidation reduction by saying oil rig. Okay, and you can always refer to it as oil rig. Oxidation involves loss of electrons, while reduction involves gain of electrons. I think that's an interesting catchphrase to remember in an exam. So we are saying redox, explained in simple terms. Oxidation is loss of an electron, and it causes reduction, meaning that a material which is undergoing oxidation itself becomes a reducing agent, while reduction is a gain of electrons. So since it is gaining electrons, where are they coming from? They are coming from somewhere. So that material which is gaining an electron by itself becomes an oxidizing agent. Okay. So we do have specific terminologies we use to make specific references to material to the redox reactions as they occur. So like for example, the oxidation process, one reactant loses electrons and the reducing agent is oxidized and oxidation numbers increase. Examples as are given over there. Zinc, a solid reacting with a proton or an acid to give zinc 2+, and the proton picks up the 2 electrons and bubbles off as a gas. We saw that yesterday when we were doing an experiment in the previous session, when we were adding a magnesium ribbon to hydrochloric acid. That the reaction resulted in the liberation of hydrogen. So we already talked about balancing equations, half equations, and we emphasized what happens in acidic conditions and also what happens in basic conditions. So I'm not going to repeat this. It's just an issue of you practicing with different so the next time we meet, we are going to explain types of cells and distinguish them between voltaic or galvanic cells and electrolytic cells, and go into the fine details of their parameters and also the calculations involving the charges that are generated at each electrode between these cells. Ladies and gentlemen, I hope this gave you a very strong background which we are going to use in our next session and then as we answer typical examination questions. Thank you very much.